So I think moving not away from, but in addition to thinking deterministically, we have to train engineers to think non-deterministically in order to make those solutions. And I don't think it's two separate people. I think embedded engineers just need to add one more skill to their tool chest, and I think that's fine.
Easier.
And I'm heading off to Aceda in a few weeks.
Yeah,
it's true.
It's a unicorn of a great
just
AI
one more
programmer and a great embedded engineer, a great C++ embedded developer. Plus, this is a great profile.
Hi, I'm Shawn Luke from DigiKey, and it's my pleasure to be here today with Davis from NXP Semiconductors, Marcus from STMicroelectronics, Neelam from Microchip Technology, Ashish from Silicon Laboratories, Robin from Nordic Semiconductors, and special guest Shawn Hymel to discuss what every developer is thinking about, Edge AI. Thank you to all of our guests for being here. Now let's talk technical. I want to start talking about how Edge AI is being used. We're surrounded by Edge AI applications, from speech recognition on smart home devices to predictive maintenance in industrial equipment. Ashish, for the first question, I want to throw it over to you. Where do you see Edge AI doing a good job of replacing traditional algorithms? And where do you see Edge AI currently falling short?
So I think Edge AI is doing a really good job in areas where traditional rule-based algorithms starts to fall apart because the real world is messy, right? Let me give an example. Let's take an audio application, things like class break detection. Now, the problem is that with traditional threshold-based methods, you'll likely struggle with false positives in real-world environments because the same event might look different depending on the distance between the object and the sensor, the ambient noise, and you can get a lot of signals that accidentally look like close enough to trigger a rule-based system. So traditional algorithms don't generalize too well to that, so you end up chasing false positives. With Edge AI, the models are much better at learning patterns in noisy data because you're learning it across multiple features and over time, not just fixed thresholds. And all of this ultimately improves, accuracy and battery life. And Shawn, sorry, what was the second part of your question?
Yeah, I was wondering about where things are falling short.
Yeah, I think where Edge AI falls short today, it's less about the capability, but it's more about practicality in embedded systems. Like what I mean by that is there are multiple challenges. One big challenge is data. So Edge AI works best when you have good representative training data, and many embedded customers simply don't have that, right? Their environments vary a lot, and collecting or labeling a data at scale is hard. So when the data doesn't match reality, models can underperform in ways that are difficult to predict. Another challenge is the operational complexity or complexity of deployments, right? Running inference is the easy part. You also have to think about training, validation, updates, and long-term ownership of the model. And that's a much higher bar than traditional firmware, especially for teams without the machine learning expertise. And then lastly, I would say I come from a firmware background, so I can appreciate the value of predictability and debugging. With traditional algorithms, when something goes wrong, you can usually point to a specific condition or a parameter. But with machine learning models, especially highly optimized models, behavior can be harder to predict at times, which makes some customers cautious, particularly in embedded systems where reliability and being able to debug on a hardware is critical. Um, all that to say is I don't see Edge AI as a universal replacement. I think it's extremely powerful when applied to the right problems, but that success comes from being selective, using machine learning where it clearly adds value and keeping the rest of the system simple and predictable.
If I can add on to that, I think you absolutely nailed it with where they're falling short, where it can be difficult to deploy. And that idea of the ops side is absolutely something that keeps me up at night for how do we deploy? How do we make sure something's personalized to your particular environment? So I think you absolutely nailed it there. So to summarize kind of what you were saying with that last part, I think you're absolutely right because I see edge AI as complementary to traditional algorithms, where you're doing things like, let's get a fast Fourier transform, let's do some filtering. And you see a lot of, especially on embedded systems, a lot of cases where you're developing a feature extraction that's human derived, like getting the like doing the fast Fourier transform, the meld frequency cepstral coefficients for speech recognition and so forth. You're doing a lot of that deterministic stuff up front, then you're going to the AI portion, and that helps for a variety of reasons, such as like keeping your things small, keeping your model small, making sure you have less data going through, and you know what's going into the model because it's replicating, say, how humans hear or how humans see. So it's complementary, and like you were saying in that first part, it absolutely is going after some hard problems that traditional algorithms couldn't tackle in the first place. So things like image recognition, which has been traditionally very, very difficult, and doing things like sensor fusion, where we had these traditional algorithms, but then we can just shove data from multiple sensors into the inputs of a model of say a neural network, and it just kind of figures out the patterns and relationships between those sensors to make it work, assuming, like you said, we've got enough data and we know the space we want to deploy it in.
Excellent. Davis, I want to send it over to you. What are some common stumbling points as AI gets deployed at the edge? What are you seeing?
Yeah, it's a great question and pretext for maybe some of the further conversation today. I think the example and the way that she's described where rules-based systems fall short and what the necessity is. It's not about maybe, necessity is mother of invention, right? And so I think that's why people have moved to these neural network type approaches at the edge. So it's come with benefits. It's also come with shortfalls, as the question implies. I would say it depends on the nature of your application. So if you're in one narrative that has been empirically kind of observed in practice as well as, okay, the previous neural networks, I don't want to call convolutional neural networks like resonant and stuff that are still used legacy neural networks, but the previous wave of RNNs and LSTMs and CNNs and fully connected models were more compute bound. Now we're in an area that's very memory bound. And what the new area I mean is transformer-based architectures, and what autoregressive models have done have lots of benefits, right? That's where they've vastly surpassed anything you could do from a rules-based system for modeling language. It's truly remarkable. But at the edge, and for the deployments where rubber meets the road, literally for automotive use cases, where inference becomes the bulk of the market demand, that's where the move from compute-constrained workloads to memory-constrained workloads has really started to show where edge AI deployments can fall short, because it's a non-starter. If you don't have the physical capacity, if you don't have the right engine for the car, you're not going to get very far. That rhymed kind of nicely, actually. But all that aside, I'd say that's one of the biggest shortfalls. And so, of course, the silicon providers like ourselves and others have risen to meet this gap and this need with new products, new inference engines, new compute platforms. But that fundamental block remains the same. I think the real shortfall. We mentioned MLOps stuff. We mentioned data drift. We mentioned probability distribution is changing. So how do you architect your system to create these updates to the ML model plus the firmware plus code updates as well has been something that there's been a huge everything from observability tools to optimization workflows, etc. But I'd say we're moving into an era with the right compute at the edge where human creativity becomes the limiting factor. We don't want to be in a world where we're constrained by, I don't have enough memory, or I can't afford the memory, or I don't have enough power supply at the edge. If we can move past those barriers, then it's like, well, what can you think of for your business or for your own interest that you could deploy that we can power?
Yeah, I would just like to add something to that answer. Davis answered it really well, the common stumbling points that we have today. And I think when we talk about memory, another challenge is like the device constraints, which Shawn touched on. Like when we are training the model, we are often running a full precision model, right? At the edge, you really have to quantize, you have to compress, you really have to optimize it to fit into those RAM and flash budgets that you have. And sometimes that means that the model you deploy doesn't perform exactly how you saw it in the lab or on your PC, right? That's, I think, one stumbling point. And for edge devices, we also see that the system interaction is another factor that you have to keep in mind. Machine learning doesn't run in isolation. It interacts with the power management unit. It interacts with wireless stacks, the RTOS scheduling. So small changing in timing or power states can really affect latency and even the model behavior.
Yeah, if I can chime into this discussion, I think agree with everything that's being said. I want to draw attention to the other end of the spectrum, which is getting the data right. That is also a big stumbling block. So if you think about where edge AI is successful today, it's a mobile platform. You got a Face ID on your Apple iPhone and so on and so on. But there's enough compute power, but also it's a heavily concentrated application where if you get it right, you get millions and billions of units that come through. And so there's enough amount of investment being done and enough efforts being put in. What happens in what we call thousand beachfront war, which is a motor control system or a home appliance systems, you have a unique problem that are thousands of them. They're all different. And so in order to get edge AI right, you not only have the constraint on silicon where your compute and memory, as discussed, is restricted, but also getting a good quality data. What is that you're trying to make intelligent about, and getting a data set that allows you to make that intelligent feed into the AI machine. That is an even bigger stumbling block. And that's the one that's not going to be easily solved by throwing money at it. It's going to be solved only by human ingenuity and hard work behind it as it goes through over the next 5, 10, 15 years in all those devices.
This is a great conversation. What I'm then wondering, I'm going to send this over to you, Robin, is like, what edge AI applications do you see that are production ready currently? It's kind of part and parcel of this discussion that's going on. Not only that, but then kind of a second part to that question too. Where do you think things may be changing in the next 5 to 10 years? Any applications that you think are like on the cusp that might be ready to start going production ready?
Yeah, so where I come from, it's all about ultra low power in the terms of energy consumption. So it's not necessarily about what can be done with AI, but what can be done at the very edge of the network, because edge AI spans all the way from on the sensor itself into a edge server, which it has 1,000 times more of the processing capabilities. But in Nordic, we mainly do things that are on the sensor side, very close to the user or the input data. So one good example that I can think of is this smartwatches and activity trackers and smart rings and things like that. For the last probably 15 years, all of the step counting algorithms, for example, has been based on machine learning. Whereas before that, 20, 30 years ago, they were based on some threshold from a manual programming exercise. And what we saw was with those less advanced techniques, it was really easy to fool these step counting algorithms. But now it's almost impossible for you to make your smartwatch register something that isn't an actual step as a step. And for ultra low power like this, it up until now it has been very much in the vibration space. So everything from vibrating machinery for predictive maintenance, things like gesture controls for remotes, and everything that's relating to this type of accelerometer data and vibration sensing. We also have a lot of asset tracking application that uses vibration to detect when it is necessary to connect to the cloud to send data. So if you can take the local decision that this is an anomaly, you can save a lot of bandwidth and also in that energy from not connecting to the network as often as you would if you would always send data to the cloud.
Yeah, and also to build on this, I think you mentioned it's a very wide area. I think it's in the consumer area. You mentioned like wearables and so on, and then I think also I see a big run in industrial. And I think one example I want to mention is what is kind of a lot of people don't think is, and I think those goes back what was said at the beginning, is like arc fault detection. So when you have like in your home, when you're switching big loads or in solar systems, solar inverters, you get arc faults and they can basically burn your house down. And I think with traditional algorithms, it was very hard to detect those kind of events. And this is also where we're seeing a few customers actually really deploying systems which use AI, and they work much better. And then you also mentioned like in the industrial area, but also the home area, a lot of where we see is, and this is kind of like not the absolute low end, but also not really the super high end, is like vision-based system, like quality inspection, but also doorbell cameras to detect, okay, is it your dog or is it a neighbor or is it a burglar? So I think there is a lot of applications where people actually don't know or don't think that edge AI is involved. And I think also, I think the technology having more performance, better low power, I think this really helped to make this really move edge AI from a proof of concept to really operational and basically a mass market application. And I think that happened in the last, I would say, 3 to 5 years. Probably.
Marcus, I think that was very, very well said. I have a former colleague who's working on responsible AI at Microsoft. A few years ago, he told me, we've been told to stop trying to make up models to do stuff. Just think of what to use the models for, because we have the models that can do the things we need them to do for enterprise tasks, for detecting all this kind of stuff. This is less PC, but like let's say edge AI, but more PC. But I think as Robin mentioned, that itself is a big spectrum from gateway to microcontroller to sensor edge. But I thought that was a very interesting frame of view, right? And so I think it makes what that does, it makes edge AI itself also very latent, and that's a powerful thing when it's pervasive but latent, because it doesn't feel like technology. It does the thing you want it to do.
I think for us, it's not about what you can do with edge AI, because everything that you could do with edge AI, you could do in a data center with AI. It's about how much of it you can move towards the edge and how far towards the edge you can move it. So it was interesting how you mentioned the voice assistants a little bit earlier, because all of these voice assistants, they are trained to recognize only one word. They are trained to recognize their own name locally. And once they recognize their own name, they start streaming all your audio data to the cloud. And this is probably covered by their terms of service, but it's not very good for privacy, and it's not good for your bandwidth, and it's not good for your power consumption. The biggest problem that you can solve is that you can actually make all of these things more practical for the user. So you don't have the bigger power drain by always turning on your radio to stream the data to the cloud. You don't have privacy issues because all of your all the noise from your inside your home is going to a cloud server somewhere, and you don't need to worry about any of those things. So as long as you can push things towards the cloud, it saves you a lot of headaches.
I like this, Robin. I really like where you're going. And yeah, there's so many different layers to it, whether it's latency or privacy, but like the overall getting to that user experience and it actually being driven by needs and necessity being the father or the mother of invention there in that space. I wanted to pivot us a little bit and then start talking about how these edge AI solutions get built. So I'm thinking about things from the developer standpoint, things like the software development kits, things that used to be called TensorFlow Lite. I think it's now called Lite RT, to SaaS solutions like Edge Impulse, as people are building, training, developing models, and then going out in the field and running them. Can embedded engineers work with non-deterministic systems like Edge AI, or does there need to be a clear division between embedded engineers? And do you think there needs to be a separate discipline kind of brought into the field with just ML developers working at the edge?
So maybe I can jump in. I think all the development kits play a very critical role in enabling, whether it's ML engineer or embedded engineer, to really achieve the goals in the time frame which is realistic, practical, etc. Right? Without a good quality toolkit that's well put together, an engineer can struggle and the project can go haywire. That doesn't mean the toolkit is everything. You know, as we talk about, you need to address the problem by making sure A, the problem merits to address, B, you're able to think through the whole thing about data collection and what's the outcome you're looking for. Are you looking for deterministic outcome? And if so, how are you going to put the constraint to be able to get those deterministic outcome, and so on and so forth. And once you have that flow right, toolkit is there to help you. And of course, you have to choose the right toolkit which allows you to achieve the goal. Not every toolkit is well prepared and meant for every types of use cases, unfortunately, because every company and every toolkit has a kind of specific tune and focus. All of them eventually may become general purpose enough to address all different kind of problem, but by default, a consumer oriented silicon company will have created kind of models and environment that looks very different than an industrial oriented company. And so you're going to find those variations at least for a while, and you have to pick and choose the right one.
I, I completely agree. And Shawn, to maybe keep adding to that question about how these projects get started and what they come to life. I think for silicon companies, because this is where our POV mostly, it depends if you have a customer that's coming from an upgrade pathway, so they bought a previous MC or MPU and are now looking at an AI gen product. Sometimes there's totally new. If you're in mass market, so we have a long tail of some 20,000 plus customers, and that's cool because you see a lot of exciting products, but from an AI non-fragmentation consolidated toolchain perspective, it's a near impossibility to have a single push button for all the AI needs of all those customers. But how these things get built, I think concrete examples often help. So I'll bring one example just to try to add this question. We had an interesting avionics use case where they had heard about RAG, so retrieval augmented generation, to fine-tune LLMs. They obviously heard about LLMs and ChatGPT, this AI thought leader at the company. They're an existing customer of non-AI silicon products, and now wanted to do this kind of pilot's manual in a speech interface, so they could take this 3,000 page PDF about an aircraft and compress it into a database for an LLM using RAG. That was the idea they heard about through Hugging Face and these kind of very developer ecosystem tools, and now wanted to bring that to the edge silicon by way of working with us. To make that come to life, as Nilam was describing, is this really fragmented, piecemeal approach. And I think that's why people think of edge AI technologies as a solution looking for a problem, because if you just look at model compression or a compiler or just this MCU with an MPU inside of it, you're like, okay, what does all these individually solve? Well, actually, not that much, but altogether they can solve exactly that problem I just described of like an AI co-pilot for a commercial airline pilot.
I'd heard of Microsoft Copilot. I didn't hear of a Copilot for your next flight.
Yeah, exactly.
If you don't mind, I just want to add on to that real quick with from an academic perspective, because there's a high level thing going on here where I think as embedded engineers, as firmware developers, we are trained to think deterministically. We have to count instruction cycles. We look at our tosses and go, can we meet our super tight deadline? And we spend all this time thinking about these really, really tiny deadlines, and can we meet these? And is it deterministic? All that's fantastic. So I think there's another piece to this where if we're training embedded engineers, we have to also get them to think non-deterministically. Take a probability and statistics course just so you can think in terms of that, and then make sure you're super clear with your business cases over, is 90% acceptable for the outcomes of this? Is 99% acceptable, right? We're not, a lot of times this isn't flying something to the moon where we have to have exact math to, get into orbit. This isn't that. This is we just want to know about how many people come into our store, so we're making a people counter, and it is 95%, identifying people acceptable. If so, great, then your solution wins. So I think moving not away from, but in addition to thinking deterministically, we have to train engineers to think non-deterministically in order to make those solutions. And I don't think it's two separate people. I think embedded engineers just need to add one more skill to their tool chest, and I think that's fine.
Easier.
And I'm heading off to a CETA in a few weeks.
Yeah,
it's true.
It's a unicorn of a great
just
AI
one
programmer and a great embedded engineer, a great C++ embedded developer. Plus, this is a great profile. That's a very expensive profile too.
I think that's going to be the new thing.
Prompt engineer plus.
I agree with your point that with embedded engineers to learn more about machine learning and be okay with those statistics. I think it also really depends on the type of application you're looking at. If I'm looking at a normal step counter, I'm fine with that accuracy. But if I have a pacemaker, then I'm not fine with that accuracy. I need that exact precision. So I think that distinction becomes really important in context of the application that you're looking at.
Hey, Marcus, I want to get you involved here. What would you say, kind of a spicy question here, like, are SDKs actually accelerating innovation, or are they creating vendor lock-in?
I think so. To base on the discussion we just had, I think SDKs help a lot to make like the traditional embedded engineer basically to make it easy for them to basically get into a machine learning and create the models without basically being a data scientist. So a lot of the tools right now, like if you call what are specific SDKs, they do have like auto ML features, or they or a lot of the companies like also ST, we have like model zoos. So we offer like pre-trained models which then customers can adapt. So I think using those SDKs actually more as an advantage for the engineers and for the companies to get edge AI deployed much quicker than because yes, embedded engineers can do it. And this goes back to the discussion is that kind of also if you look at what nowadays is taught on school. So when I went to university 30 years ago, there was nothing about the AI. But now I think if you go to an EE grade, you can choose AI classes. So I think the profile of an embedded engineer also changes over time. And I think coming back to your original questions, I do not see an SDK as a problem with a vendor lock, because I think it's for specific applications you use an SDK, and then I think if you have a different applications, you might use a different approach to create your model.
So I actually feel a little bit opposite about the SDKs, is that they are doing the opposite of vendor lock-in, because when we talk about SDKs for embedded development nowadays, it's or at least the ones I'm most familiar with, they are building on these RTOSes, and they are mostly supporting open source RTOSes. So the one I'm most familiar with is building on the Zephyr RTOS, and that is the opposite of a vendor lock-in, because there's many of our competitors are also using the Zephyr RTOS and supporting it. So it inherently makes applications built for our hardware more portable than they used to be. And with AI specifically, or Edge AI specifically, there's a lot. The most used frameworks are open frameworks as well, like LightRT, for example. That is also not locked to any one or few vendors. It's something that anyone can use as long as you have a Python toolchain. You can make a TensorFlow model and then optimize it for LightRT and run it on any hardware. So I'm still thinking that the SDK or the framework that you're using for Edge AI is actually the opposite of a vendor lock-in.
Robin, I'm glad you said that. But sorry to cut in, but I think the only counter example to that point, which we're all familiar with those frameworks, the most kind of historic vendor lock-in in AI is probably CUDA, and probably what that's done for, like GPU abstraction. For our end of the market, for serving, the lower the cost of friction to switch vendors, which comes to the SDK, helps reduce vendor lock-in, right? So it's like if you have PyTorch or Executorch or ONNX, which is open no exchange, running equally across all these MPUs, you're going to choose off of other things: cost, relationships, risk, trust, whatever. But one of the most historic vendor lock-ins ever has to be CUDA, which does the opposite of what you described. Because I was trying to think while you were speaking, I was like, it's kind of almost entirely true. But then
I love seeing the push for a lot of open source frameworks like Zephyr. As somebody who has a Zephyr course out there, love it. I think what Zephyr's trying to do is super cool. That being said, I also think Davis is right in the sense that not just CUDA being vendor lock-in, but there are so many companies have HALs and SDKs, and then what ends up happening is that Zephyr's actually built on top of those. So Zephyr's calling into those.
Yeah,
it's an abstraction layer. Yeah, it's not replacing the vendor HAL. It's just providing that abstraction layer that people can develop on. And what I think Zephyr's doing is great, but you pay for in terms of, resources required on your system, learning time, and all of that. So you still, even as an embedded engineer, you still have to make the choice of, hey, do I want the leanest possible thing? In which case, I'm just going to go straight to the vendor HAL and learn that. And now
the
we're
convenience
probably
part, like Noam was saying, yeah.
And you still have that. So there's still a trade-off you still have to make. And I'm seeing both. When it comes to NPUs, I'm seeing companies adopt either the ARM IP cores with the Ethos cores, or they're rolling their own. So I think I know ST has theirs. I think Nordic has one. And so now you're locked into their framework. or you go for the ARM one. And that's not necessarily easy to use either if you're using like Vela or Mera to compile and quantize your models. So, right, we're still seeing this kind of fragmentation. And do you end up being locked in because now you have the SDK and this pipeline to deploy your model? That looks like one thing. My hope is that we can just, take a TF Lite file or an Onyx file and we give it to some kind of Zephyr thing and it creates this wrapper around Zephyr and now it's, completely portable. But it's the embedded world, which means that will incur costs, and that's always a trade-off you will have to make.